All right. But if you have any questions, just feel free to unmute yourself. All right, welcome to AI612 Machine Learning for Healthcare Week 3. We're gonna continue on with predictive modeling and the whole process. And so starting from the start of the previous week, we are going to talk about three things: the tasks, the data processing, and the modeling. And we've covered so far 2 prediction tasks, which are hospital readmission prediction and ICU readmission prediction. Then we took a look at the workflow example. So working with the actual raw CSV files, and if you wanted to do hospital readmission prediction or ICU readmission prediction, how you would approach the tables and which information that you would extract from each tables. And this week, hopefully, we can cover the remaining 3 topics: the MapReduce, which are just a big data processing framework mainly for data processing. It's not for machine learning. And then modeling part, which I'm going to talk about the classical approach using logistic regression, and the deep learning approach using RNN. Actually, no, before that, I forgot to, we actually didn't quite finish the workflow example. Sorry about that. Right here. Actually, yeah, let me reshare the screen again. Yeah. So last time we talked. So the last time we actually looked at the hospital readmission prediction and how we would extract information from the tables. So so 5 tables. The hospital readmission prediction task is obviously it's a hospital level thing, so we looked at 5 admission related tables, which were admissions, and we extracted these information, and we looked at the Python data structure using triple nested dictionary, and the last dictionary had 3 lists in it, which were diagnosis list, medication list, and the procedure list. Then we extracted gender information from patients, and then diagnosis codes from diagnosis ICD table, procedure codes from procedures ICD table, and the drug names or formulary drug code from the prescriptions table. And using those 3 codes, we populated 3 lists, and finally we sorted the second inner dictionary, which are the admissions, which contains the admissions per patient, so that sorting them by the admission time or admit time would allow us to figure out who becomes which admission becomes a positive case for readmission. So that means that after this current admission, another admission happened within 30 days after discharge. So that's why we sorted the admissions by the admission time. So using that, we were able to distinguish or label which ones were the positives and which ones were the negative samples. Then the final output would be a list of admission objects. So admission objects being the inner or the second inner dictionary. So which would contain, actually no, I'm sorry, the innermost object, the innermost dictionary, which would contain these information here, that would be individual samples, the training samples, which would have readmission label as the target label. So the final output was a list of admission objects. So it doesn't concern the subject IDs anymore. So we no longer care about the patients. So that was hospital level readmission prediction, and it was time to take a look at the ICU level readmission prediction. So based on the red information here, so will this patient visit ICU again within the same hospital stay? So as I said, it's totally fine in practice to use information from if you were at time here, then it would be okay to use information from all paths, so including this blue bar here, or if you had access, maybe anything that happened within here as well. But for the sake of simplicity, we're gonna just I'm just gonna show example where we only use this information that occurs within this red strip, the ICU state. So the task is using information that occurred within this red strip, and then trying to predict whether this patient will be admitted to the ICU again within the same blue strip, which obviously here for this patient is for this red strip is a negative case. So there were a lot of ICU related or ICU level tables. There were 8 tables, but again, for the sake of simplicity, we're just going to use 2 tables to go and just take a look at the examples. So ICU stays, which the ICU stays table, which just records the time, like who were admitted to the ICU and what time they were admitted and what time they were discharged, and that kind of just administrative information. Chart events is I've said this before, but this contains like several hundred millions of rows of information, which amounts up to like 25, maybe 30 gigs of the raw CSV file. So basically, everything that happens within the ICU, like the devices that are hooked up to the patient that monitors heart rate or respiratory rate or SpO2, which is 산소포화도, body temperature, blood pressure, all that kind of stuff that is like constantly monitored over the entire stay is all stored in this table. So that is why it's such a large table. So we're going to use just 2 tables here, ICU stays and chart events. And let's take a look at the ICU stays first. So ICU stays, so here you can see that HADM ID, which is the same ID from previous example, which is the hospital admission ID. So before, and of course, we will need ICU stay ID as well, because we're looking at the individual ICU records as a single sample. So obviously we're going to need this, but why do we need this? It's the same rule. So in order to know which samples are positive cases and which samples are negative cases, meaning that which one did end up with readmission and which did not. In order to know that, we need to know the hospital level ID as well. It's the same rule, but before, when we were doing hospital level readmission prediction, we had to know the subject ID as well as HADM ID in order to sort the admissions with admit time. So we're going to do the same thing here. We're going to first group the individual ICU stays with their corresponding hospital admission ID, and then sort the ICU stay with in time, which is the admission time. And of course, there's out time, which is when the patient was discharged from the ICU. And then there's LOS, which is length of stay. So how many days the patient spent in the ICU. So we're just going to use these 5 information. So it's the same thing. It's the triple nested dictionary. So there's hospital stay at the top, and then in the hospital admission ID, HADM ID, would be the first key, and then the ICU stay ID would be the second key, and then within the innermost dictionary there would be 1, 2, 3, 4, 5, 6 fields. So in time would store this information, out time would store this information, LOS. And we have, just like the diagnosis list, medication list, and procedure list from the previous example, we're going to have chart items and chart values. So these 2 lists will be populated based on the information extracted from the chart events. And then, of course, we will need the Y label, which is the readmission label, which is set for 0 for now. So let's take a look at the chart events. So chart events has a lot of information, but we are only going to take a look at just 4 features or 4 columns here. So obviously we're going to need HADM ID and ICU stay ID in order to access the innermost dictionary. So we need this key and this key so that we can populate these 2 lists. So they are here. And then item ID and value number is what we're interested in. So item ID is the type of information that is stored in the chart events. So like item ID 1 could be blood pressure. Oh, actually that's not too accurate. So item ID 1 could be respiration, the respiratory rate, 호흡 수, and then item ID 2 could be heart rate, the 심박수, and item ID 3 could be body temperature. It's like that. It's just basically just a bunch of integers that correspond to some certain features or information extracted from the ICU, the actual ICU devices, the monitoring devices. And the value number here would be the actual number, the value for that feature. So like your body temperature could be 36.5 degrees Celsius, and your respiratory rate could be like 15 or 20 per minute. What else? Like your blood pressure, your diastolic, systolic blood pressure could be like 60 and 100, something like that. So basically, that's all we need for this example. There are a lot of side information like chart time. Chart time is when this item or this feature was stored in this chart events, and there are several other things like value in string form, value in integer form, value in like the number form, but we're going to use value in number form. Value UOM is the unit of measurements, like the milliliter or liter or deciliter, that kind of stuff. But so in order to obtain really accurate information, you need value num and value UOM at the same time. But we're just gonna, for the sake of simplicity, again, we're just gonna assume that the UOMs are all the same. Like if it's blood pressure, it's always gonna be mmHg, not something else, like not CMHg. And if we're gonna look at I don't know, body temperature is always Celsius, not Fahrenheit, something like that. So we're just gonna assume that the unit of measurements are all consistent and just gonna extract the numbers only. There are some other information, but we're just gonna ignore them for now. So the item IDs would be used to populate chart items list, and the value numbers would be used to populate the chart values list in the innermost dictionary. And then same deal. So same deal as the hospital level readmission prediction. So we're going to sort the individual ICU stays under the hospital ID using the in time. So we're just going to sort them, and then use the ICU. So obtain the ICU list, and then use the ICU list to iterate through the hospital system, iterate through the individual admission IDs in temporal order, so that we can label which ones are the positive, like the positive being 1, and which ones are the negative. So the readmission label would be labeled correctly. And then the final output would be the same deal, a list of ICU stay objects. And now this thing doesn't really concern with the subject IDs, the patients, and then the hospital IDs. So the final outcome is it's just individual ICU level information. So that would be like one ICU stay amount equals 1 training sample. Right, so that's the second example of going through the tables and then extracting information to construct your data structure. Obviously, this kind of data structure is not yet ready to be used for machine learning, obviously, because in order to train a machine learning model would be it logistic regression, support vector machine, random forest, or RNN, CNN, transformer, whichever, everything needs to be in a vector form or matrix form, to be more precise, because we're going to use mini batches. So we need to vectorize this information. So this information is for human readability purposes. So it's easier to understand if you have this kind of data structure. Then you can, once you have this information, which will be your training cohort, your study cohort, actually, because you're going to study the ICU stays readmission prediction. So once you have these information populated, then that's going to be your raw source of information, and then after this, you're going to have to vectorize this with another another process. So the whole pipeline is just extracting information from the raw CSV files to construct the data structure, and then once you have the data structures, you have to vectorize it, and then once you vectorize it, you can train a machine learning model of your choice. So that's the whole pipeline. All right, so that was okay. That wraps up the previous week's material, and we're going to move on to this week's material. Actually, wait a second. I'm sorry. Let me reopen. Oh, here it is. Okay. By the way, any questions so far? I hope that the examples were pretty much straightforward. Yeah, I'm going through all the examples because a lot of new machine learning researchers or junior machine learning researchers, they are so used to downloading the training set or training data set and then just simply plugging them in, or not even downloading. They just call the data set using the PyTorch command, and then they just plug that into the machine learning model, and then just use the backprop to train the model. So, but in EHR, as I said, there is no universally used data set for training your model. So you need to actually look at the data, and then you need to have your own definition of, you need to set a goal, what you want to do, what kind of prediction you want to do, and then you need to define which information you want to use. So it's much more like, you need more practice to become like a stand-up data scientist, basically. So, right. So that's the whole purpose of actually the reason behind going through the examples one step by and another step. Okay. So again, as I said, so we've completed 3 topics so far, and then today, hopefully, we can complete the MapReduce introduction, and then maybe we can cover classical approach as well. All right. So today's topic, MapReduce and modeling common So hopefully, today's topic, data pre-processing using MapReduce, and then modeling part. So whether you use classical approach or just or RNN or CNN or transformer, whichever approach you use, you still need one common preparation. So we're going to talk about that first, and then after that, we're going to talk about logistic regression. So MapReduce is I'm not sure if anybody here is familiar with MapReduce, or if there's actually an undergrad course that teaches MapReduce, maybe in the data mining introduction class. So I'm just going to assume that nobody is familiar with MapReduce here. So MapReduce is used for processing a really gigantic amount of data. So a data that would not fit in a single machine, or not even a single workstation. So we're talking about data that amounts up to maybe hundreds of terabytes, or maybe what's after terabyte? It's tera, exa, a peta, yeah, something that amounts to like petabytes, or maybe even exabytes, or something like that, or zettabytes or something. So basically, just the data itself is so humongous that either one, it would not fit in a single machine, or two, processing, even if it fits in a single machine, processing it would take such amount of such a huge amount of time that you really need to you need a distributed computation to actually finish the job in a reasonable time. So that's where MapReduce comes in, and it was developed quite some time ago. Actually, I think it was developed in. Now we're going to talk about the history of MapReduce maybe a few slides later. So just go through the conceptual example. So let's say that we want to find a keyword from text data. So there's like a huge, there's just like a heap of text, There's just a lot of text data, raw text data, and then we want to find how many times word case occurred in the text. So then what we will do is simply just use the grep. If we're using a Linux or Unix-based machine, then we're just simply gonna use the grep function, the grep function to grep, like, grep double quotation cast, and then go through the text, and then it will just retrieve the total number of instances that where case occurred, and then that becomes your count. The count of how many times the case occurred in the text. So that is when you have a small amount of text, and when you have a huge amount of text, a text that does not fit, the amount of data that does not fit in a single workstation. What we used to do before MapReduce is just split the data into several pieces and then distribute it to multiple computers. So they're not even like, hooked up like a cloud or anything. It's just you have a bunch of computers in a network. Like you're a company and you have like a server, you have workstation number 1, workstation number 2, workstation number 3, all hooked up in a like a corporate network. And then you distribute this gigantic data into each workstation, and then each workstation would have now a amount of text that is able to that can fit into each workstation. Then you use grep in each workstation to count the number of times case occurred in this smaller text, and then you take the matches, which would be a much smaller information compared to the actual raw text. The number of times case occurred is just like orders of magnitude smaller than the original information. So you have the essential information from individual workstation, and then you pull them into one master workstation. So you merge the information, and then you have now the actual the total number of counts that case occurred in this original gigantic text. So that is the traditional way. So this is a bit burdensome because you have to manage the text. You have to distribute it into the workstation and then run the script over all workstations, and then again merge the information from the individual workstation, and then you can present your final outcome. And this is hard to maintain because once the text increase, like the new information arrives in the original text, then you have to decide which workstation you want to send that to. So it's there's a bit of an overhead in the managing perspective. But as long as you have many workstations, this is easy to just configure. Right, so that was the old way, or the traditional way, and MapReduce is a bit similar to that, but it handles a lot of processes automatically. So it's an automatic distributed data processing framework, or it's not even a framework. It's just like a philosophy or an idea. So the idea behind MapReduce is there's again a gigantic text that might not fit in a single workstation. And then there in MapReduce, it always comes with a virtual file system. So if you are familiar with Hadoop, then there's HDFS, Hadoop file system. So it's kind of like a cloud these days. So you upload your text into the virtual file system, or Hadoop file system to be particular. So HDFS, and you don't need to decide. So actually, in order to MapReduce, all the computers must be hooked up into a single network, and then they compose a coherent single virtual file system. So the computers are all wrapped with a virtual file system. So once you upload your information, your text information to the virtual file system, then they're automatically distributed across different workstations. Or from now on, I'm just going to say nodes, because there's usually in MapReduce, there's worker nodes, and then there's the master node. So the master node is responsible for managing the tasks and uploading and downloading the files or whatnot. So, and then the nodes is where an individual nodes or the worker nodes are responsible for actually storing the data and then actually doing the work. So it's like there's master and then the working horses. So again, as I said, so you upload the text into the virtual file system. So you don't need to care about which file, which text piece is stored in which workstation or which node. It is handled automatically. So the load is balanced automatically. And then of course, there's like a replication factors in order to maintain a high throughput. So for example, if you replicate your entire text into 2 texts and then distribute across the nodes, then there's like a smaller chance that what you're looking for in each individual nodes are always there. So it's like a high availability type of thing. But anyway, yeah, that's all handled like under the hood, so you don't need to really care about it. But the only thing you need to remember is that it is taken care of automatically. So they're once they're in the virtual file system, you can actually write a map function and a reduce function. That there's 2 stages. There are 2 stages. So there's the map phase and the reduce phase, and that's the reason behind the word MapReduce. So the map phase is where you write a function that works on individual nodes, and individual nodes possess their own text pieces. So individual nodes can work on the possessed text pieces using the functions that you wrote. So once you write the map function, it is replicated or distributed across the entire worker nodes, and then the worker nodes will just copy the map function and then work locally using its own text pieces or data pieces. So it's completely parallel and distributed fashion. So there's no communication in the map phase actually, or ideally there should not be any communication between the nodes during the map phase. I think you can enforce it. So it's been quite some time since I studied Hadoop, but ideally if there are no communications between the nodes, that would actually speed things up. So map phase is completely local phase. So here, for example, what we could think about is just counting the number of times Keist occurred in this text. So what you would write in the map function is simply just going through the text line by line and then just matching using regex, or just simply find key using just find command or whatever to count the number of times Keist occurred in individual text in individual nodes. So once you have that, then there's the reduce phase. So reduce phase is once the local parallel tasks are complete, you need to merge and do some after the post-processing of the information from the map phase so that you have the final outcome here. So it would be like merge. So basically, what you would do in the reduce phase typically is merging the outcome from the map phase and sorting them or grouping them or filtering them or ranking them, that kind of stuff. So if the task was simply counting the number of times Keist occurred in the entire text, then what reduce phase does is just simply merging the information, merging the counts from individual map tasks, and that's it. You just merge the information, merge the counts from the map phase, and then simply sum them up. So all reduce phase does is just summing the counts from this phase, and then finally that will just present the output to the user. So this all thing like virtual files, the loading loading or copying the data into the file system is done automatically. I mean, you have to copy it, but load balancing, all that is done automatically. Assigning jobs to the nodes for the map task, it's done automatically. You just write the map, and then you just execute the map task, and then the functions will be replicated to the nodes automatically. And then the reduce phase is also done automatically. You just write the reduce function, and then the reduce, like the shuffle and all that, this whole thing, this whole process here would be taken care of automatically again. So everything is more or less like semi-automatic. So this is the actual example of word count. So this time we're not just counting the number of times Keist occurred, but we're just counting the number of times all words occurred, or all unique words occurred. So here there is 3 lines of text, which is Dear Bear River, Car River, and Dear Car Bear. So we have this, and then ideally what we would want is the outcome like this. So bear occurred in the entire three lines. Bear occurred twice, car occurred 3 times, deer occurred twice, river occurred twice. So the number of times each unique word occurred in the entire text. So that's the setup. And imagine that this is such a gigantic text that does not fit into a single machine. So MapReduce does what it does is first you just copy this entire text into the file system, and then it'll be automatically split in the unit of lines, individual lines. So like when you upload the original files into file system, the individual lines would not be cut into like sublines. At least a single line would be stored in a one node coherently. So here in this example, 3 lines are split into 3 machines. So it's 3 machines or 3 worker nodes. So deer, bear, river, car, river, deer, car, bear. And then the map phase, what you would write in the map phase is you just go through, you tokenize the sentence into words, and then you just simply count the number of times each word occurred in the given text. So here you tokenize this into deer, bear, river, and then individual words occurred 1 time. So deer 1, bear 1, river 1. In this case, car 1, river 1. So you don't even have to merge the car 1 here. It will be all taken care of in the reduce phase. So you just simply count car 1, river 1, and then again deer 1, car 1, bear 1. Now in the reduce phase, in order to merge the information which word occurred how many times, you need to actually set the keys and values, where the keys would be the unique word or the word itself, and then the values would be the number of count that key occurred in the data. So there's a bit of a shuffling phase where each words are grouped by their actual, so the words are grouped according to the unique words. So all the bears would be merged here into bear 1, 1. So bear here, there's bear 1, there's bear 1. So these 2 bear 1, bear 1s are merged into a single list where the key becomes the bear, and then the value list becomes 1 and 1. So bear 1, 1. Same thing happens to car. So there's car. So car 1, 1, 1. Deer 1, 1, river 1, 1. So it's the shuffling phase. And then after this, there's the reduce phase. So reduce, the reason behind the word reduce is actually because you're reducing the information into like a smaller dimension. There was a list here. You can see that there's a list, but now all you need to do is just sum the elements of the list in order to acquire or obtain the count. So you're reducing the list into a scalar. So 1, 1 becomes 2, 1, 1, 1 becomes 3, 1, 1 becomes 1, 1, 1 becomes 2. So now there's 4 reduced tasks. So bear, car, deer, river, and then after the final result will be just a simple aggregation of the reduced outcomes. So just bear 2, car 3, deer 2, river 2. So know that the number of map tasks and the number of reduced tasks don't have to be the same all the time. It can be actually completely different. In this example, there were 3 map tasks, so meaning that 3 nodes might have been used to perform the map tasks, but there are 4 reduced tasks. So theoretically, there could have 4 worker nodes might have been used to do the reduced tasks. So hopefully this is a clear example. So the reason that the word count example is so frequently used to present or describe the MapReduce workflow is because it was actually MapReduce was actually invented in order to do this kind of stuff, this massive text processing. So it was developed by Google actually. So and it was developed in order to construct an inverted index. So if anyone's familiar with search engines or crawling and that kind of stuff, hopefully they're familiar with inverted index. For those who are not familiar with search engines, just as a high-level description, inverted index is what you use to let's see. So once you give let's say that you go to google.com and then you search for what else? like deep learning. So you search for, the query is deep learning. So there are 2 words. And then once you enter deep learning into the search engine, it could be Google, but it could be anything. Like it could be DuckDuckGo or it could be Naver, but whichever search engine you use, once you enter the query, search, like for example, deep learning 2 words, then that given query would be matched or would be used to go through the inverted index. So inverted index. So you see the inverted index is it's just a key value index, and then where the keys are the words. So in this example, deep learning, you search for the deep entry in the index, and you search for the learning entry in the index, because as I said, the words are the keys in the key value inverted index. So you go to the deep entry, and then in the deep entry, there's a like whole list of documents that are relevant to the word deep. And then in the learning entry, there's again in the value side, because it's a key value index. In the value side, there's a list, like whole list of like millions of documents in the list, ranked by the order of importance or relevance to the word learning. So once you have deep learning, then you have like you can do a bit of like a set operation to figure out which documents are in the high ranks or in the highest of ranks in both the deep entry and the learning entry, and then you present that document to the user. So that's how search engines are operated. So in order to actually construct the inverted index, you need to go through the text first. You need to go through the text, being the web pages, the HTML web pages. But because what Google does is it crawls millions, maybe trillions, or like like infinite number of web pages throughout the web, and then Google stores that crawled web pages into the virtual cloud system, and then they have to actually go through individual web pages to figure out what the contents of the web pages are, what the web page is talking about. So it is basically natural language processing or text processing. So it needs to go through it tokenizes the web pages into the words, and then it counts the number of words. Basically, it's word counting. So it counts the number of words, and then figure out how many words occurred in the web page. So in order to do that, MapReduce is like a very nice tool to do that. So that's why the Google actually came up with MapReduce, because if you think about the number of web pages in the web, there's no way Google can use a single workstation to go through all the web pages and count all the number of words, and then it's just impossible. I think there was a question. 맵주스기, 네, 안성용님, 맵주스 기법은 분산처리로서 의미가 있는 건 전체 연산을 줄어드는 건가요? So the question is MapReduce only useful for distributed, performing tasks in a distributed fashion, or does it actually help reduce the number of computations or the amount of computations? And the answer is it only is useful for distributed computation. It does not actually reduce the amount of work that needs to be done. So it just reduces the amount of time to complete the task by using a lot of computers, basically. Hopefully that 답이 되셨나요? 네, 감사합니다. Right. So actually, another good thing about MapReduce is it doesn't need a dedicated, really expensive servers. So before MapReduce, in order to do a gigantic jobs like counting words in trillions of text, trillions of web pages, IT companies such as IBM or Sun Microsystems or that kind of companies, they usually built a really gigantic dedicated server that costs like millions or maybe billions of dollars. Just one single machine that has a lot of CPUs, that has a lot of RAMs, that has basically just like supercomputers. But what's good about MapReduce is you can actually hook up just workstation level computers, and that's it. So you don't need a dedicated supercomputers. You don't need to build a supercomputer. You just buy you can buy maybe hundreds or maybe thousands or maybe tens of thousands of just ready-made computers or workstations that are a bit more expensive than personal computers, like computers that cost about $10,000 or $20,000, 몇 천만 원 하는 워크스테이션들 있잖아요. 그런 거를 사가지고 줄줄이 엮어서 이 MapReduce 시스템을 만들면 됩니다. 그냥 옛날처럼 막 뭐 수억 원짜리, 수십억 원짜리 슈퍼컴퓨터를 만드는 게 아니라 그냥 상용 컴퓨터를 사서 엮어가지고 만들어도 MapReduce를 돌리는데 전혀 지장이 없어요. 그러니까 이제 굉장히 혁신적인 시스템이죠. So yeah, so that's why Google developed MapReduce, and they still use it internally. When I was in Google, I still use MapReduce, but it's no longer. I don't think it's no longer called a MapReduce. It's called something else. I mean, but the basic philosophy is still the same. There's the map phase and the reduce phase, but it's more advanced. There's a lot more tools and a lot more steps you can fine tune or you can customize. But the philosophy or the idea of MapReduce still persists to this day inside Google. And so once Google built this, there was an open source project a few years after Google started using MapReduce, which is called Hadoop. So it's an Apache Hadoop project. So it's an open source version of MapReduce. I'm not sure who built this. Yeah, I'm not sure who built this, but basically they knew what MapReduce is. So Google actually announced the MapReduce technology. So someone inspired by that decided to write a Java version of MapReduce and open source it using Apache as an Apache project. So Apache Hadoop is written in Java, and it's based on read writes to local disks. So MapReduce is actually developed to to handle massive amount of data. So obviously you can't store that data into RAMs in that memory. So basically the MapReduce is based on read writes from local disks, the hard disks. Or if you're rich, you can use SSDs as well. I think there was another question. Oh, someone from Yahoo. Yeah, I think so. Someone named White, like Tom White or something. It's been such a long time since I studied Hadoop, but I think Hyungjin, Hyungjin is right. The reason that, just a funny story, the reason that it's called Hadoop is after the developer who wrote Java, he had a son, and the son had a toy, a doll, not a toy, like 그 인형 있잖아요, 인형, toy. And a toy that was a elephant toy. 그 이제 코끼리 인형인데 코끼리 인형의 이름이 하둡이었대요. 그 자기 아들이 이제 코끼리 인형 이름 하둡이라 지어서 그걸 보고 그냥 하둡이라고 했다고 합니다. So yeah, the Hadoop is the name of a doll, that the developer of MapReduce's son had. So Hadoop was quite a thing back in early 2010. So 2008, 9, 10, 11. I think I used Hadoop really a lot when I was in ETRI, the 한국전자통신연구원. So when I was working there as a researcher, I used Hadoop a lot in early 2010, 2011, until like 2012 or so. And then a few years after Hadoop was released, there was Apache Spark developed by the people from Berkeley. So Apache Spark is again, it's a MapReduce thing, but it is based on memory, not hard disks. So it's obviously much faster because everything is loaded onto memory. So the spirit is the same. You have a bunch of computers, the workstations, or maybe individual like personal computers, all hooked up into the Hadoop system. And instead of storing the data into local disks, you store the data into local memory. So the memories are used to construct a virtual file system, the cloud. And then you do the same thing. The MapReduce is all the same. Sorry. And as opposed to Hadoop being written in Java, Spark was written in Scala. So it's a functional programming language. It's a bit different. But it also supports, I think Spark supports Python and Java as well. So if you have, obviously, so if you have a bit smaller data to process compared to, like crawling trillions of web pages, maybe you have just a few gigabytes of data or a few terabytes of data, then you can simply use Spark to speed up the entire process. I think the IT companies a lot of IT companies, maybe in Korea, IT companies as well, they use, or at least what I heard from the colleagues from the United States, a lot of companies actually do use Spark a lot in order to process data, pre-process data, or process data, or basically just the companies that have the database and then the data to store and data to load and data to analyze, they use Spark a lot. So if you're interested in the whole MapReduce thing, it might be a good idea to start with Spark first. I'm not sure if Hadoop is used really frequently these days. And once you learn Spark, this will definitely come in handy when you actually, apply for a job at an IT company, or actually you become an engineer in an IT company. But as far as MapReduce goes, this will be the end of the introduction. Actually, I have a few more introductions, but I'm not going to actually go through the Hadoop and Spark, technologies. It's up to you guys to actually study on your own. But just as an example, how you would use MapReduce when constructing the data structure for ICU readmission task. So what you would start with is you would split the ICU stage. So like splitting the individual lines into the nodes or into the clouds, the file system. You would start with splitting the ICU stage. So you have individual ICU stages, and then what you would do is you would process in keys and values, because as I said, everything is processed in key value once you go to the shuffle stage and the reduce stage. So you actually have to define what are going to be the keys and what are going to be the values. So the keys would be HADM ID, because you need to actually oh, we don't have it here, I'm sorry. So you have to use the hospital admission IDs as the key, because you need to merge them or group individual ICU stays with the corresponding hospital admission keys, so you can sort by the in time and then label which becomes readmission positive and which becomes readmission negative. So key, so the HADM ID becomes the key, and the values become ICU stay ID, in time, out time, LOS. So these are the three features that we can extract from the ICU stays table. And then you shuffle with key. So each HADM ID, if there are multiple ICU stays within a single hospital stay, then when you shuffle with key, then what you would see is this kind of example. So one single HADM ID associated with a list of ICU stays, like one key associated with a list. So one key associated with a list, but where the list items or the list values become this example here, this tuple, 3-element tuple. And then you do the reduce. So when you do the reduce, the hospital stays. Wait, I'm sorry, hospital stays. Oh, okay. So when you're doing the reduce, actually here we're not reducing by the HADM ID, but we're reducing by the a bit more. Yeah. Here, what we did is we reduced by the individual keys, and it's in the same manner we're reducing by the hospital stays. So hospital stays, HADM ID was the key. Now we're reducing by the same hospital level thing. So HADM ID, like here, like bear 11 becomes bear 2, like car 11 becomes car 3, and deer 11 becomes deer 2. In the same manner, we're merging them with with the same hospital admission ID. But actually, we need to sort the HMID this pair here, this 1 2, this 2 line becomes a single unit within the reduce function. So one unit and 2 unit. So we need to sort the units based on the in time X, so that we can actually decide which becomes the positive and which becomes the negative samples. So the reduce function actually comes with a sort function. So you can do a lot of stuff in reduce. As I said, you can sort, you can merge, you can filter, you can group, you can do a lot of stuff in the reduce function. But here we need to actually sort based on the in time value here in order to distinguish, in order to make the labels. Same here as well. So you, in order to actually so this example was processing the ICU state table. This here is processing the I'm sorry, I think, yeah, my Wi-Fi was actually disconnected for some reason. Can everybody hear me okay now? Yeah, yeah, 그 공유기가 갑자기 그냥 뭐 안 돼가지고 지금 일단 테더링으로 지금 그냥 땜빵 하고 있습니다. 이상하네요. Now, okay, so going back to the chart events, so as I said, chart events is of like 30 gigs or something, so it would probably not fit in your laptop actually. So like chart events is like a nice example where you can take advantage of the distributed power of MapReduce. So if you're interested, you might like chart events chart events plus the Apache Spark would be a good combination to start with learning the MapReduce thing. So in this case, we would split the chart events to several lines. You know, the lines, like individual lines would be uploaded to individual like nodes, and then again processing keys and values. So key would be H, ADM ID, ICU stay IDs. We need 2 keys in order to group them into individual ICU stays. So we need to like later merge this information with this information. You know, so we need to merge this information, the item ID value num with this information. So that's why we're using 2 keys here. So the values would be the item ID, the features like the blood pressure, temperature, the respiratory rate, heart rate, that kind of stuff. So that would be the item ID, and then the value number would be the actual values. Then you process in keys. So what you would do is you just simply extract these information in the map phase. You extract these information. So you extract the keys, you extract the values, and then once you have them, you package them into keys and values so that you can use them in the shuffle stage. So in the shuffle stage, these the tuples can be keys. So this tuple becomes a key, and then it is associated with a list of item ID value num tuples. So and then you have the reduce phase where you have the in like a lot of individual units. Typically, a single ICU stay is consists of like at least hundreds or maybe even thousands of item IDs and value num pairs. So this list here would be this data structure would be humongous. So it's not, there's just only 2 units of information here, but there would be like at least hundreds or thousands, and then you would have to merge them with either previous data structure here, or you can pre-process them separately and then just manually merge them in the local hard drive at the last stage. That's up to you. Right, so that's the that's the end of the MapReduce introduction. Hopefully the idea behind MapReduce is conveyed, but of course the details you would have to study on your own. Any questions so far? No. Did anybody actually learn MapReduce in the one of the undergrad courses? I'm just wondering if there are actually courses that teach MapReduce. 없나요? MapReduce를 학교에서 배우시는 분이 아무도 없나요? 나 데이터 마이닝 수업. 데이터 마이닝 수업은 그 신기정 교수님 데이터 마이닝 수업 말씀하시는 건가요? 그럼 적어도 학부에서는 안 가르쳐 주나 보네요. 네, 알겠습니다. 사실 굉장히 좀 그 IT 업계에서는 아주 만연하게 쓰고 있는 건데, 네. 제가 구글에 있을 때도 제가 다뤘던 그 병원 데이터들의 양이 엄청 어마어마해가지고 이것 도저히 이 맵리듀스를 안 쓰고서는 이 트레이닝 셋을 만들 수가 없었거든요. 그래서 그때도 이제 뭐 원하지 않았지만 울며 겨자 먹기로 맵리듀스 코드를 막 C로 짜고 그랬었는데, 여러분들도 나중에 혹시 그런 뭔가 대량의 데이터를 이용해서 뭐 트레이닝 셋을 만든다 그러면은, 뭐 특히 구글이나 뭐 페이스북이나 아마존이나 이런 데 가시면 그쪽에서 보유하고 있는 데이터는 뭐 당연히 상상을 초월하죠. 근데 그런 거를 해서 어떤 소량의 어떤 머신러닝 학습을 위한 데이터를 만든다 그러면은, 그거를 라인 바이 라인 훑어가면서 하면은 1년이 걸려도 모자랍니다. 그래서 당연히 이제 맵리듀스를 쓸 수밖에 없는 때가 올 수도 있죠. 뭐 네이버 같은 데서 당연히 아마 쓸 거라고 저는 생각을 합니다. 네이버든 카카오든 뭐 다 당연히 보유하고 있는 데이터가 어마어마하니까. 네. Alright, so the next thing is modeling. So hopefully we have about 20 minutes. Right. Alright, so look again before we go into the details. So common preparation. So whether we use classical approach like logistic regression, or whether we use RNN or CNN, we have to do one thing, which is actually vectorization. So as I said, the data structure itself is not suitable for using them as a machine learning training set. So obviously you have to do the data preparation, but and of course you have to split the data into train, validation, test set. Hopefully everybody here, the participants, are familiar with basic machine learning knowledge, and hopefully they took the programming for AI class last semester. So I don't have to go into detail why splitting data is necessary. So if you're not familiar with like train, validation, test set, please let me know. If not, I'm just gonna skip the details. So it is used for end-false cross-validation. One thing that we might want to consider is preserving the positive-negative sample ratio. Usually in healthcare predictive tasks, the class is severely imbalanced, because just naturally there are way more healthy people than there are sick people. So being sick is a kind of a rare event. So if you just sample the patients from the actual population, like for example, people who have cancer, it's less than 1% of population, maybe less than. So if I know correctly, the number of people who are diagnosed with cancer every year is less than 300,000. 30만 명이 안 될 거예요. 제가 만약에 봤다면. 그 말은 이제 1%가 안 되는 거죠. 이제 물론 뭐 총 암 환자의 수를 생각하면 1%가 넘겠지만 어쨌든 굉장히 적은 수입니다. So as I said, the number of like people diagnosed with cancer every year is less than 300,000. So that's like a lot less than the entire population, which is 50 million. So being sick itself is a rare event. So the positive negative sample ratio is severely imbalanced. So when you split the data into training, validation, test set, you might want to care about preserving the exact ratio in train, validation, test set. So if the entire population in the entire data set, the positive negative sample ratio was 9:1, like 9:1, and 9:1, then you might want to preserve that ratio in all train, validation, test set as well. So take care about being a bit more considerate. And then you need, of course, the mapping between string values into the integer values. So all machine learning models require numerical input. You can't put obviously you can't put string values inside it. So for example, the ethnicity, we did extract ethnicity information from the admissions table. So the ethnicity value would be Asian, Black, Hispanic, white, or whatever, Native American. Like I think there were like quite a lot of ethnicity values in Mimic 3, but they are all string values, so they can't be used to. You can't feed string values into neural nets or logistic regression, so you need to convert them into integers. So Asians could be 0, Black could be 1, Hispanic could be 2, white could be 3, and then like yada yada yada. So that they become categorical values actually. So you need to, once you create this, you need to remember, or you actually need to store this mapping information somewhere as a text file. So the Asian 0, black 1, Hispanic 2, white 3. So when you actually train the network, and then when you do the like the feature attribution studies and that kind of stuff, you can actually know that 0 is actually Asian and 1 is black. So creating the string integer maps. So for example, here, not all features or not all information must be, or actually to be more precise, each feature must be handled differently according to their modality or according to their value types. So here, the times here, admission time, discharge time, they are actually times. So you need to process them separately. You want to maybe normalize them by days, or normalize them by hours, or normalize them by years, or, you know, that's up to you. It depends on the task that you're performing. And then the admit type here, the admission type is, as I think I briefly explained about this, but there are several admission types. One is just you walk in by yourself. You make a call, you make a phone call to the hospital, and then you walk in, or you're admitted to the emergency department, like you collapsed and then you are like you are transferred to the admission, the emergency room, and then from there you are transferred to the ICU unit. So that's another type. So the types these are discrete values. Marital status, of course, this is also a discrete valued feature. Like you could be divorced, you could be single, you could be widowed, you could be married, or complicated, whatever. So it's a categorical variable. Ethnicity, categorical variable. Gender is either 0 or 1, at least in the mimic3 case. So it's a binary value. Admission diagnosis. So this is the reason for being admitted. Like, you know, you had like I don't know, you were shot, or you fell and you broke your bone, or you had like acute something, like 급성보가 생겨. So again, this is categorical variable. So these are all semantically, they can be multi-label thing. Like you could be Asian and black at the same time, or whatever, or you can be married and or you could be married and single. I don't know, like could be complicated, but just for the sake of simplicity, everything here is going to be just categorical. You could be only one ethnicity. You could be only one marital status. You can have only one admission diagnosis. That makes the whole thing a bit more simple, straightforward. And here, this is where multi-label setting comes in, because you could receive multiple diagnoses, you could receive multiple medications, you could receive multiple procedures within a single hospital admission. So they are now actually multi-label things. Readmission, you're either readmitted or not. So it's a binary thing. Okay, so these 1, 2, 3, 4, 5, 6, 7, these information must be mapped to, because they're all strings. Admission types are strings, marital status strings. These are all string values, so you need to convert them into integers. So for example, admit time, we're gonna just ignore how you would process the time for this, at least for this example, because you can do it on your own. Here, so the emergency divorce white, like this is the data structure given to us, and once we have a map between the string values and the integers, then we can map them into integers. So emergency becomes 1, marital status 3, ethnicity white was 3, gender 1, and then like chest pain is like 12. Then the diagnosis code list, like 4109 4280, they become, so because they themselves are strings, actually, because if you are familiar with ICD-9 codes, there should be a dot here, a decimal point, 410.9, 428.1.0. So that's actual diagnosis code. So they're strings, and you need to convert them into integers again. And then warfarin, D5 double vancomycin, they are all integers. And again, procedure codes are also strings, so you need to convert them into integers. And then the readmission one, they are intact. So this is what you would have after you convert all your strings into integer information. No, integer types. Then what you would do is you would need to vectorize them. So again, excluding the time information. So admission type 1, this information here has to be converted to a vector in order to be in order so that you can plug them into your downstream machine learning model. So suppose that there are 3 admission types. There's elective, which is you come in on your own, and emergency, and other. So let's say that there are 3 admission types. Then obviously you need to prepare 3-dimensional vector where everything is 0 except for one, except for one element being the second element here, because elective would be 0. Elective would be mapped to integer 0. Emergency would be mapped to integer 1. Other would be mapped to integer 2. So since emergency, since we want to represent this information, which is 1, then we will need to tick the 0. We need to change the 0 to 1 for the second coordinate or the second dimension. So they become, this information becomes 0, 1, 0. Marital status. Let's assume that there are 5 marital status types: single, married, widow, divorced, and other. So here, the original information was divorced, and that was mapped to 3. So we convert this into a 5-dimensional vector where the 4th dimension is 1 and all the others are 0. Same with ethnicity. Assuming that there are 4 ethnicities, then this becomes 0, 0, 0, 1. Gender, this is just a 0 or 1, so it doesn't need to become. I mean, if you want to, you can actually represent them into a 2-dimensional vector, but we don't have to. Admission type, let's assume that there are 14 admission diagnosis types. So this becomes a 14-dimensional vector where the 13th dimension becomes 1 and all the others are 0. The rest are a bit straightforward. So let's assume that there are totally 10,000 unique diagnosis types, because there are actually a lot of diagnosis codes in the ICD-9 system. So there are 10,000 diagnosis types. So you need to prepare a 10,000 dimensional 0 vector. And then since you have 422 and 3214 as the multi-label information, so you need to set the 420 the dimension that corresponds to 422, which is 423rd dimension, and 3215th dimension, you need to change them to 1 and all the others are 0. So this will be an extremely sparse vector, because out of 10,000 candidates, only 2 are active. Same with medications. There are usually about 20,000 medication types. So you need to prepare a 20,000 dimensional vector, and then you need to tick the 3 corresponding dimensions: 6, 4, 1, 2, 2, and 1, 5, 3. Again, a really extremely sparse vector. Same with procedure list. Again, assuming there are 10,000 procedure types, you prepare a 10,000 dimensional vector, and then you tick 1 element that corresponds to 2, 1, 4, 2. Okay, so you've converted all categorical or multi-label variables into vectors. Then what you can do is, what you need to do is actually you need to represent this entire data structure, this information, into a vectorial form, a vector form, so that becomes a single example with the label y become 1. So you need to prepare an x the vector that represents the features x and the label y. So you simply concatenate all the vectors that you've prepared so far. So the admission types, marital status, ethnicity, gender. There would be 14-dimensional vector here for the admission types. Then another extra 10,000 dimensions, extra another additional 20,000 dimensions for medications, and 10,000 dimensions for procedures. So in all, it would be about 40,000 dimensional vector that represents a single hospital admission. And then you have a readmission label set to 1. So you can imagine that out of 40,000 dimensions, only 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Only 11 out of 40,000 dimensions, only 11 are active. So which is too sparse, basically. So if you are familiar with the lookup tables, maybe you can use the PyTorch or TensorFlow lookup tables to reduce the waste of memory and waste of space, because obviously this is a waste of space. But for now, we're just going to assume we're just going to stick to this in this example. We're not going to use like lookup tables or anything. We're just going to stick to this example, which is way more intuitive and way more straightforward. Right. So this was the hospital readmission prediction example. So because this is a hospital level thing, that is why we converted the hospital admission information into the vector form. But if we are to do the ICU readmission prediction, then we need to convert this ICU admission data structure, this information, into the vector form. So, which we would do about mostly the same thing. So actually, fortunately, there aren't too many categorical variables here. This LOS, length of stay, is actually a continuous variable. So this is how many days you spent in the ICU. So for example, in this example, the patient stayed 2.4, like 2.5 days almost, about 2.5 days inside the ICU. The thing of interest to us is the item list and the value list, actually, because typically when you're in the ICU, same items or same events occur multiple times within the ICU stay. For example, here 4280 891 891. So 891 occurred twice. 1814 occurred once, but 7712 occurred 3 times. So this is a bit different from this example here. So in the hospital admission, diagnosis list, medication list, and procedure list, they contain unique events. There are no duplicate events in the hospital. This is, I mean, obviously this is pretty obvious, because when you are discharged from the hospital, when they write a summary, they don't actually write the same thing multiple times. 그러니까 이제 병원에 가서 퇴원할 때 그 환자가 겪었던 어떤 뭐 진단을 감기 걸렸습니다 이렇게 안 쓰잖아요. 감기 걸렸습니다 딱 한 번 쓰고 뭐 수술을 받았습니다 딱 한 번 쓰고 이렇게 하지. 이거 여러 번 쓰지 않는단 말이에요. But as opposed to that, when you're in the ICU, you take body temperature measures like multiple times. Well, I think this is Fahrenheit body temperature. So is that correct? I think this is Fahrenheit body temperature. Right. So yeah, let's assume that 7712 is body temperature. So in the ICU, actually, you are measured your body temperature multiple times, maybe even like dozens of, or maybe hundreds of times if you're in the ICU for like long stays, if you're in there for like longer days. So this is completely natural. Like the same event could happen multiple times, and obviously the values would change. Like when you first take the body temperature, it would be 101.2 degrees Fahrenheit. Then the next time you take the body temperature, it would be slightly different value. And I think this could be maybe some kind of body blood pressure. So like first time you take the blood pressure, it would be 68, but then the next time, maybe 5 minutes later, or maybe 1 hour later, when you take blood pressure, it will be 72. So this is completely natural. So we need to take care about how we would process this or convert this into a vector form. So if you do the same thing as before, like here, if you just prepare a high dimensional vector with the number of dimensions being the same number as the unique number of different measures or different features, and then you just simply tick the dimension that corresponds to the one active here, that wouldn't be appropriate in this case, because here there are so let's assume that there are maybe, okay, so example is 15,000 item types. So there are unique 15,000 item types, and you want to tick the dimensions that correspond to 7712, but there are 3 7712 occurrences. So how you would do this? Would you set this to 1, or would you set this to 3, or maybe something else? And how would you prepare the vector for the value list as well? Because if you set this to 3, then how would you pack this 3 list of values into a single dimension here? Would you average them, or would you sum them, or would you take the min value, or would you take the max value? So these are all things that you need to consider. So if you want to be really naive, then what you would do is you would simply just tick this to 1. So instead of actually setting the value 3, you just set the value to 1, just to indicate that this value was measured. And then you would just average these information. You would just take the average and then put the value here. So that would be like, so semantically, what you would get is, out of 15,000 item types, this was measured, and the average value was this. Same deal would go with here. Like, this value was measured, and the average value was this. For the others, it would be not average, it would be the actual value. So that's how you would prepare a vector form, or vector, like the X feature vector for this, out of this ICU admission data structure. Right. So hopefully this makes sense. So when you actually do the projects, you would have to care about how you would process the data. It is up to you. There is no definitely right answer. It's all up to you. But I'm just giving you the details so that you don't get frustrated, or you don't get confused when you actually encounter this kind of problem. Now this is a bit more auxiliary information. So let's assume that how you would actually derive the patient representation. So far what we did is we derived the admission vector, admission representation. So how we would derive or obtain a single vector for a single hospital admission. So single hospital admission being the blue strip here, blue strip that we so far talked about. And then here we talked about how we would obtain a vector that represents the single ICU admission, which is a red strip inside the blue strip. But what happens if we want to derive a patient representation vector where the patient has multiple blue strips, meaning that the patient was visited the hospital multiple times over the entire lifetime. So in this case, the patient went to the hospital 3 times in his lifetime, or in her lifetime. So then we could, following the same formula, same method here, we could obtain individual 40,000 dimensional vector for each blue strip here. So this will be 40,000 dimensional vector. This will be 40,000. This will be 40,000 dimensional vector. And somehow, let's say that we want to maybe predict whether the patient, whether this patient is a cancer patient, or whether this patient will receive cancer diagnosis in the future, like here, or sometime in here or something. So, or something like, basically something that we want to predict based on the patient level, not the hospital level, not the ICU level, but the patient level. Then how would we aggregate or merge these 40,000 dimensional vectors into a single fixed size vector, so that we can push them into the predictive model? So yeah, this is for capturing longer dependencies. Longer dependencies meaning like multiple hospital visits, and this would be appropriate for patient level prediction tests such as chronic disease or cancer predictions or that kind of stuff. So there would be, obviously there's no right answer here. There's a lot of infinite number of answers here. So how we would derive a single fixed size vector out of these 40,000 dimensional vectors? First of all, we can just simply sum them. We can just sum these 3 vectors to derive a single 40,000 dimensional vector. So that is obviously that is obviously a solution. Or we could average these 3 vectors and then obtain a single 40,000 dimensional vector. Again, that is obviously also a viable option. Any other method? Care to take a guess? 어떻게 하면 될까요? 뭐 다른 방법이 있을까요? 이제 단순히 더하거나 그냥 뭐 평균을 때리는 것보다 뭐 또 다른 방법을 쓸 수가 있겠죠, 당연히. 네. 뭐 맞추실 분이 없으면 돼. 뭐 예를 들어서 우리가 프로젝트를 할 때에도 당연히 쓰겠지만 RNN 같은 걸 써도 되겠죠. So we could actually use the RNN. So we could plug this into the time step 1, this vector into time step 2, this into time step vector, this vector into time step 3. Then the final hidden vector at time step 3 would actually be a patient representation vector. And same goes with either using like one-dimensional CNN or transformer or whatever. Whichever neural network function that you use, it's all up to you. But basically, all we need to do is based on 3 vectors, we just need to obtain a single 40,000 dimensional vector. So that would be the basic process. All right, I think we are almost out of time now. So unfortunately, we couldn't get into the classical model part, which is how to use logistic regression to do the readmission prediction test, which would be straightforward because since you've hopefully most of you already took the programming for AI class last semester, so you could easily imagine how we would use this information, use this information to do the prediction tasks. But we'll just I won't go into detail. So in the next class, I won't go into detail what the logistic regression is. We'll just take a look and then just how we would train them, and then how we would analyze the result, and then how we would measure the performance. So that would be it. All right. Right. Okay. All right. So this is the end of the class. Any question? No. All right. As usual, if you have any question, you can post them on Classroom, or you can send me or the head TA or any TAs an email. And all right, I'll see you guys this Thursday. See you later. Bye bye.